Hello everyone. In this lecture, let us see what are the limitations of overcurrent relay. So let us consider a distribution line of a feeder line. So let us take the generated EMF is fed to the feeder is E and its ZS is a source impedance. So let us take the fault point as here, right? At point A, the fault has been occurred. So if you consider the fault current at any instant will be equal to the amount of generated EMF divided by ZS, right? Where ZS is a source impedance. If we consider if ZS is constant, that is source impedance is a constant one. Now the amount of fault current is E by ZS. So this ZS is constant, but the place where the fault has occurred, depending upon that, the total impedance is differed. That means the impedance corresponding to the line where up to the instant where the fault has been occurred will be getting added to the source impedance to find out the total fault current, right? So now let us take a three-phase line fault is occurring, that is triple L fault has been occurred. So if it is occurred here, you can E by ZS, let us take this is a triple L fault, L fault. So in this case, see the fault current is very high. As you know, it is the most severe fault. So the fault current will be high. So if you plot a graph between the fault current and the point where the fault has been occurred. So if the fault has occurred far away from the bus bar, so the amount of fault current also goes on reducing, right? So next, if it is a case of double L fault, so now the amount of fault current is very less compared to the triple L fault, so that the amount of fault current will be reducing. The ratio of E by Z is also reducing. Same as the case of LG fault. So here in this instant, the amount of fault current is still less. So now if we want our relay to operate, the minimum amount of fault current must be greater than I pickup value, right? So it will be designed to operate up to a certain instant of current. So that will be I pickup value. Now this is the I pickup value is constant. So the relay starts operating when this I pickup line coincides with this fault current line. So this is the instant where it is coinciding with the LG fault current, and this is LL and this is triple L fault. That means you can say that the instant up to where the relay operates is only up to this instant, so that we can tell this is a reach of LG fault. Reach of the relay for LG fault. That means this relay can operate only up to this distance. So depending upon the place of occurrence of the fault, the operation of the relay is being influenced. So that means the amount of impedance is affected by the relay operation. That means IF depends upon the type of fault. Point number 1 is IF depends upon the type of fault. So depending upon the fault, the impedance is varied. Depending upon impedance, the fault current is varied. Right? That means as the severity of fault is going on decreasing, the relay operation is varied. So now let us consider, before we have considered source impedance is constant. Now let us consider the fault at a single place, that is at bus bar, and also source impedance is variable. Now if source impedance is variable and the generated EMF is constant, then also the fault current is changing, right? Depending upon the source impedance. So if source impedance goes on changes, then fault current goes on changes. If fault current goes on changing, the intersection of the fault current line with the pickup value is also changing, right? So that means the distance up to which the relay is operated is varied now depending upon the type of the fault. So we can conclude that IF depends upon source impedance also. Also you can observe the fault current is also dependent upon the generated EMF. So if generated EMF is variable now, then also the fault current is changing. If fault current is changing, again it depends upon the reach of the fault, right? Reach of the relay or reach of the fault. That means depending upon the fault current, now the relay operation of the relay depends. Fine. So the limitations of overcurrent relay, we can conclude that it depends upon the relay operation, depends upon the type of the fault. So it also depends upon the source impedance, and it also depends upon the generated EMF. Now we cannot estimate in a power system where the fault can occur. That means the relay, whatever we are using, it must be able to operate, or it must be able to clear any type of fault, irrespective of the instant, irrespective of the place where it is occurring. So, but this overcurrent relay is not satisfying that property. That means it is only able to operate only up to certain distance from which it is operating, right? So to overcome this, we need a relay which can operate, which can clear the fault at any place, irrespective of the type of fault, irrespective of the source impedance, and irrespective of the generated EMF also. So for this, we are going for distance relay. Now let us see on what concept the distance relays can be operated. Let us consider a transmission line with generated EMF E and source impedance ZS. Now let us assume that fault has occurred at a certain instant. At that time, now the CT is operating and PT is operating. To overcome the disadvantage of limitation of overcurrent relay, now if we are able to operate a relay such that it must detect the impedance of the transmission line, and if the impedance is below the Z set value or below the set value of the relay, then it must operate. So if you take a relay such that it operates like that, irrespective of the amount of generated EMF, irrespective of ZS, that is source impedance, irrespective of the fault current, then we can overcome the limitation of overcurrent relay. So now let us draw the equivalent circuit of this transmission line. So this comes as like this. The value of RL and XL depends upon the instant where the fault has occurred, right? So RL is a resistance up to the fault instant, and XL is a reactance up to the fault occurrence value. Now IR is a value of the CT, so that means the current detected by the relay, and VR is a value of the voltage detected by the relay. So now, irrespective of the value of source impedance and generated EMF, if our relay operates only depending upon the value of IR and VR, not IR and VR, it depends upon the value of the ratio of IR and VR. That means if voltage detected by the potential transformer divided by current detected by the relay, so if that is less than Z set value, this our relay should operate, right? So what happens when this operates like this? Let us see now. So VR by IR, let us take this as ZR, so which is nothing but impedance detected by the relay, which must be always less than the Z set value, where Z set is nothing but the set value of the relay at which this relay should operate. For this to happen, let us consider the torque equation. So where we have seen in the last lecture, that is K1I square IR square minus K2 VR square. So where IR is a current detected by the relay and VR is a voltage detected by the relay. So for this torque value to be positive, when it happens only when K1 IR square is greater than K2 VR square. So where K2 VR square is less than K1 IR square, so that means VR square by IR square must be less than K1 by K2, that is VR by IR must be less than under root of K1 by K2. So if we take this ratio of K1 by K2 such that it is always less than VR by IR, so this will be ZR, it must be less than, this is Z set value. That means we should set our relay such that the ratio will be equal to Z set value must be equal to under root of K1 and K2, where K1 is the constant corresponding to IR, that is current transformer, and K2 is the constant corresponding to potential transformer. So this is the case of impedance relay, right? Impedance relay. So in this way, different types of distance relays are there. So that is, one is impedance relay, reactance relay, and more relay. So of which one by one we are going to see in the coming lectures. Thank you.